Welcome to Maths with EJD. In this video, we continue with evolutionary algorithms for nonlinear programming problems. Okay, so we've talked about nonlinear programming problems and different methods like penalty method, barrier method, Karush-Kontoka conditions, and now evolutionary algorithms. So under evolutionary algorithms now, which can be used to solve nonlinear programming problems like the rest of them. We have, in the previous video, we saw simulated annealing, which is an idea borrowed from metallurgy, cooling in metallurgy. So in this case, you're going for Tabu Search. Tabu Search. After now, we'll be talking about genetic algorithm. We've seen that before under derivative-free methods, genetic algorithm. Then after this, we'll be talking about the particle swarm optimization, which is patterned after uh, behavior of fish and bird. The way they behave together, right? That school of fish and all that optimization. And then lastly, we'll be talking about differential evolution. So all of these things are evolutionary in nature, and that's due to the fact that we keep improving the search of our of our optimization result, right? So we have differential evolution. Okay, so these are the five methods we'll be considering. There are more methods, but these are the ones we're focusing on. And like I said already, simulated annealing is done. Now we're turning our focus to Tabu Search for nonlinear programming problems. So let's go for that. Tabu Search. Call that TS if you like. Okay, and Tabu Search is an optimization algorithm used for solving used for solving complex combinatorial problems, including 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 non-linear programming problems where the objective function or constraints are non-linear. Okay. Um, the algorithm is based the algorithm is based on local search with the key feature of using memory structures to avoid revisiting revisiting previously explored solutions, previously explored solutions, and to guide the search towards better regions of the solution space. Okay, so we have a bit of memory involved in this case, like the kind of idea we find in machine learning. So you remember where you've been, so you don't go back there. That's the kind of idea. So we have key components of Tabu Search. So what are the key components of Tabu Search? So we have the initial solution, just like what we have for most numerical situations. We have initial solution. There you start with an initial feasible solution, initial feasible solution. Okay. Number two, we have a neighborhood search. You can see this bears close resemblance with simulated annealing, where we do like a kind of neighborhood search. So we have neighborhood search, which involves perturbing the initial solution. So we explore neighboring solutions by making small changes to the current solution. Then from that, we make a taboo list. Make a taboo list. Here we maintain a memory structure, a memory structure, which is called a taboo list that records recently visited. I think this is the highlight of this particular method. So it records recently visited solutions or attributes, preventing the algorithm from revisiting them immediately, from revisiting them immediately. Okay. Then we have the aspiration criteria. Aspiration criteria. So this is a condition. This is a condition that allows breaking the taboo rule if a solution is significantly better than the best known solution and the best known solution. So it's more like if you're minimizing the least value you get, once you get a value better than the least you have ever got, then you displace that one. That's the idea of breaking the taboo rule. And then of course we have number 5 where we have the stopping condition. Stopping condition. So for the stopping condition, right, this could be based on the number of iterations. I mean, that's like what we have seen for most numerical processes. This could be based on the number of iterations, improvement threshold, improvement threshold, or computational time. Okay. So we have all of this in place. So let's talk about steps. Steps in Tabu Search. Steps in Tabu Search for nonlinear programming. Of course, again, we have initialization. Initialization. So with this, you begin with an initial feasible solution, X naught. And next, set the table list length and other parameters, including, other parameters like the aspiration criteria, and neighborhood structure. Then, uh, after this, we have the neighborhood search. So here, generate the neighboring solutions of the current solution, xk, typically by perturbing some variables, e.g., modifying decision variables in a small range, just like what we do with simulated annealing. Then next you evaluate each neighboring solution based on the objective function f of x. Then in step 3, we move selection. Okay, so here we the best solution, select the best solution among the neighbors, that are not on the table list or satisfy the aspiration criteria. Then after that, we can update the current solution, xk. Then number 4, we can do a table list update. Table list update. So here we update the table list with the current move to avoid revisiting this solution in the next few iterations. Okay, then number 5, we talk about termination. So of course, in every algorithm, there's a termination. Here we repeat the process for a set number of iterations. or until no further improvement is found. Okay. All right. With all of that done, let's talk about an example or so. Let's see. We have one example. Yeah, one example works. So consider the consider a nonlinear optimization problem, which is to minimize f of x equals x1 squared plus x2 squared minus 4x1 x2. So we want to minimize that. Yeah, that's just what we want to do. So let me alternate between these and this. So step one, we have the initialization. So we want to start with an initial solution. X naught, which is equal to 2, comma 1. That means this is x1 and this is x2, basically. Then we go for step two. Step two, we have the neighborhood search. So for the neighborhood search, see what happens there. So suppose the neighborhood structure, suppose the neighborhood structure allows moving in small steps around the current solution, Okay, so with that assumption in place, right? So we have to now do this. We generate neighboring solutions by perturbing the values of x1 and x2. For example, we can have x01 to be equal to 2.1, comma 1, and we can have x02 to be 2, comma 1.1. So the original thing we have is 2, 1, right? So for this first one, now we have 2.1, comma 1. So we are adding 0.1 to 2. And on the other side, we are adding 0.1 to 1. So that's neighborhood. So with this, and we can continue like that, right? We can just keep dancing around that kind of thing. So the next thing now is, since we have these neighborhoods, we can go for step three, where we evaluate. Okay, we have evaluation. So we evaluate each of the neighbors. Okay, so that means that we have f of 2.1, comma 1, which is, we have x1 squared, that's 2.1 squared plus x2 squared minus 4x1 x2. Okay, so that's simply 4.41 plus 1 minus 4 times 2.1, that's 8.4 times 1, that's 8.4. So this is simply, I mean, if we do all of this together, we have minus 2.99. I believe that's 5.41 minus 8.44. 5.41, yeah? So 8.4 minus 5.4 is 3. So that then the 0.01. Yeah. So that works. So we have this. Then on the other hand, um we have f of 2 comma 1.1. So now this is 2 squared plus 1.1 squared minus 4 into 2 into 1.1. So this is 4 plus 1.21 minus 4 times 2, 8. 8 times that, that's 8.8. So all of this will give us minus 3.59. Okay, that's another neighbor. This is even lower than the previous one. So what we are going to do is to choose. So we have to choose the best neighbor. Choose the best neighbor with the lowest objective value. So clearly in this case, in this case, in this case, we have f of 2 comma 1.1, which is equal to minus 3.59. So that implies that our x should be equal to 2 comma 1.1. Okay, so this is giving us a lower value of the 2. So we go for step 4 then. Step 4. So in step 4, we have the table list update. Table list update. Okay. So suppose the table list has a length of 3 and you add the current move. Yeah, the current move. The current move, e.g., moving from 2 comma 1 to 2 comma 1.1, which has given us a lower value. Okay, this ensures that solutions too similar solutions too similar are not revisited. Okay, so they are not revisited. Now, in this case, we now go for step 5. So for step 5, we repeat, right? Repeat the process until we get what we need. So continue the process for several iterations. So I mean, it means that from 2.2 comma 1.1, then you can still check 2.1, 1.10, 1.12, and things like that. Continue the process for several iterations, each time exploring, new neighbors and updating the solution based on the best, updating the solution based on the best non-taboo neighbor, or using the aspiration criteria. The aspiration criteria. Okay. Then we can talk about the stopping condition. When do you stop? in all this. Uh, Let me say step 6, stopping condition. Stopping condition. So after several iterations, if no significant improvement, if no significant improvement is observed, or the stopping condition, if the stopping condition, e.g., maximum iterations or improvement threshold is met, the the algorithm the algorithm terminates and returns the best solution found. The best solution found. Of course, by this time, we know that if you're going to do it manually, that is going to be a lot of work. So Python to the rescue. So let's see what Python has to say about this Tabu Search part. Tabu Search for nonlinear programming. Like you can see, we have uh 104 lines. That's a lot. I mean, you can see the process already. That's a lot. Um, so with the function is defined the x1 squared plus x2 squared minus 4x1 x2. That's the function we are trying to minimize. Then so from line 8 to 17, then we define the idea of neighbors. So we generate neighbors like very close values. So here, side step 0.1 has been used for the x. So we have x new is x copy and x new I is step size. So we just that's where the perturbation is taking place and all that. So you can study this better, copy it on Facebook and you can study and try it out on your side. Then we talk about the Tabu Search. That's where the actual algorithm goes. So we have the Tabu Search with initial solution iterations, Tabu list size, step size 0.1, best solution. We have all of this. And so we see all the initial solutions to 100 iterations. We can improve this if you want more iterations. The more the iterations, the better the results, I want to believe. Then the Tabu list size, we set it at 10, step size is 0.1. And then, if you run this, you're looking for solution between -3 and 3. That's why we have this here. So if you run this now, you get what you should get. Okay, so we can see 100 iterations done. And at the end of the day, we see the final solution to be x1 is -3.5, x2 is -3.5, and the final best value is -24.5 because you're minimizing that situation. So you can see as the search is progressing and it finally lands somewhere around here, like that. So now let's see the way it goes. 2 1 2 1, we have -3, 2 1 2 1 -3. -3 is there, and then it keeps going. We have -3.1. um you know and then I'm even trying to look for that where we had 2 and 1.1. Okay, we don't seem to have that here. So and then it keeps going. So this does its own search, and then the final result ends up as 24 -24.5. Okay, so we can take it back home and uh report the results. Okay, so we can say that from the from the Python code, we have x1, x2 to be equal to -3.5, -3.5 with f of -3.5 being the same as -24.5. So that is the minimum solution based on Tabu Search. Okay. Um, Now let's look at some advantages. What are some advantages of Tabu Search? Now that we've got the result from from Python, so let's talk about advantages of Tabu Search. So, the first one is that it is memory based. One advantage is that it is memory based. What that means is that it uses memory structures like the tabu list to escape local optima and explore new areas of the search space. Two, its flexibility is another advantage. Flexibility. So it can be applied to a wide range of nonlinear problems with adaptable neighborhood structures and stopping criteria. And the third advantage is that it is robust. So the robustness talks about that it is effective for large and complex nonlinear programming problems where exact methods may struggle. So in conclusion, right, Tabu Search is a powerful heuristic for nonlinear programming, particularly useful for problems with a complex or large search space. By intelligently navigating through neighborhoods and leveraging memory structures to avoid cycles, Tabu Search can provide high quality solutions for difficult optimization problems. So in case you have a difficult optimization problem and some problems are so difficult, you may not even find a derivative. So the traditional methods will fail in that situation. Okay. So let's talk about some practice right here. Some I'll just read out and some I'm going to write down. Okay, here are some practice questions. Okay. Um, mm, consider consider f of x equals x1 squared plus x2 squared plus x3 squared. Now this is three-dimensional. X3 squared minus 3 x1 x2 x3. So with x naught, that's the initial solution, equals 1, 1, 1. Okay. So A, using neighborhood structure, using neighborhood structure, structure that allows perturbing each variable by plus or minus 0.1, generate the first set, generate the first set of neighboring solutions. Okay, that is the first part. The second part, B, is evaluate the objective function, evaluate the objective function at each neighboring solution. And identify the best move So that means you're going to move from 1, 1, 1 to any of these new neighbors you have created that gives you the least value, because automatically it's a minimization thing we are doing, right? So then you update the current solution, and add the move to the table list. Of course, the table list is the list of solutions you are currently considering, right? Okay. Then D, repeat the steps for the next iteration. But now avoid revisiting solutions that are on the table list. That's the essence of the table list, to make you see where you have been so you don't go there again. But now avoid revisiting solutions that are in the table list. Okay. So that goes. We have that. All right. So with this in place now, we can stop here. So let me see your answer to the question on in the comment section, whether on Facebook or on YouTube. Then of course you can complete this with Python code because it is non-linear, right? It can be really tedious doing it manually. So you need your Python code to complete the process. Okay. So let me know in the comment section what your answer would be or how you go about it. So if you have an issue with this, if you also want me to solve a problem or teach a topic, let me know. I may be able to find time to do that. If you have subscribed, thank you. If you have not, please go ahead and do that. And everybody hit the notification bell so you can always get alerted each time a new video is released. Because I still have three of these methods for solving nonlinear programs problems to go, like genetic algorithm, particle swarm optimization, and of course differential evolution. We have those coming ahead. And of course, like and share so that more people can have access to this great content. Till I come your way again, keep doing math right. Bye.